Hello students, in this lecture we will discuss about the limitations of first law, the classical statements of second law, and various useful terms like heat engine, refrigerator, heat pump, thermal energy reservoir, which we will be using frequently while discussing the concepts of thermodynamics. So till now we have studied the first law, whether it was applicable for non-flow systems, that is closed systems, or it was applicable for the steady state steady flow systems or the uniform state uniform flow systems. But the basic fundamental was related to that of conservation of energy. The first law, however, places no restriction on the direction of flow of heat and work. Though in daily life we observe that spontaneous process proceed in one direction only. We will come to the examples of this thing. A cup of hot tea left in a cooler room cools off eventually. This process satisfies the first law of thermodynamics, since the amount of energy lost by hot tea is equal to the amount gained by the surrounding air. Now let us consider the reverse process. The hot tea getting hotter in a cooler room as a result of heat transfer from the room air. And we all know that this process never takes place. And even if it take place, it would not violate the first law as long as the amount of energy lost by the air is equal to the amount of energy gained by the hot tea. We may take another example. The heating of a room by the passage of electric current through a resistor. Here also the first law dictates that amount of electric energy supplied to the resistance wires should be equal to the amount of energy transferred to the room as heat. Now let us consider the reverse of this process, and it is clear that transferring some heat to the wire does not cause an equivalent amount of electric energy to be generated in the wires. A paddle wheel mechanism that is operated by the fall of a mass. The paddle wheel rotates as the mass falls and stirs a fluid within an insulated container. What happens? The potential energy of the mass decreases and the internal energy of the fluid increases according with the conservation of energy principle. The reverse process means raising the mass by transferring heat from the fluid to the paddle wheel will not occur in the nature. Although if it happens, it would not violate the first law of thermodynamics. Even we may consider the process of water flowing downhill. The potential energy of the water at the top of the hill gets converted into kinetic energy of the flowing water, and finally the water falls on the ground and the kinetic energy of the flowing water gets converted to its internal energy. The first law of thermodynamics tells that increase in the kinetic energy of the flowing water is equal to decrease in the potential energy of water while it is falling. Finally, when the water reaches the ground, the increase in the internal energy of the water is equal to the decrease in its kinetic energy. Now imagine the reverse of this process, that is water flowing uphill on its own. Applying the first law of thermodynamics, we find that it would be well satisfied if the water at the ground level was to cool by transferring its internal energy into kinetic energy, thus acquiring some velocity in the upward direction, and then the water flowing uphill by transferring its kinetic energy into potential energy. However, in practice, we never find water flowing uphill on its own. So that is, the first law of thermodynamics does not specify the direction of a process and does not deny the feasibility of a spontaneous process reversing on its own. We may take one more example. If a running car is brought to rest by applying brakes, the kinetic energy of the car gets converted into the internal energy of the brakes and the wheels. According to the first law of thermodynamics, the increase in the internal energy of the brakes and wheels is equal to the decrease in the kinetic energy of car. Now imagine the reverse of this process, that is, a car at rest starts running by cooling the brakes and wheels. The first law of thermodynamics would be still valid and says that the increase in the kinetic energy of the car is equal to the decrease in the internal energy of the brakes and wheels. However, we have never observed such thing to happen. Thus, one can conclude that first law of thermodynamics does not deny the feasibility of a spontaneous process reversing itself and does not specify the direction of a process. So on the basis of our experience, we can say that a particular process or a particular cycle that does not violate the first law does not ensure that the cycle or process will actually occur. And it is this kind of experimental evidence that led to the formulation of second law of thermodynamics. Thus, a cycle will occur only if both first and second law of thermodynamics are. So, from the arguments that we have done till now, it is clear that processes proceed in a certain direction and not in the reverse direction. The first law was placing no restriction on the direction of process, but satisfying the first law does not ensure that process or cycle will actually occur. A process or cycle will occur only if it satisfies first and second law of thermodynamics. Now, the second law also asserts that energy has quality as well as quantity. The first law is concerned with the quantity of energy and the transformations of energy from one form to another, with no regard to its quality. Preserving the quality of energy is a major concern to engineers, and the second law provides the necessary means to determine the quality as well as the degree of degradation of energy during a process. So you will be surprising that there is also some quality index for energy. For example, 100 kilojoule of energy at 100 degrees Celsius may sound equal to the 100 kilojoule of energy at 1000 degrees Celsius, because in both the case, that is whether at 100 degrees Celsius or 1000 degrees Celsius, the amount of energy we are talking about is 100 kilojoule. So they are same in magnitude. So it may sound that both are having the same quality of energy, but in the subsequent lectures you will come to know that the energy index associated with the 100 kilojoule of energy at 1000 degrees Celsius is more than that with the 100 degrees Celsius. With the interconvertibility of various energy into another forms, several questions arises in our mind. Is it possible for the complete conversion of internal energy into work in a heat engine, or is it possible to devise a heat engine the efficiency of which is equal to 1, means 100%? Is it possible to transfer energy as heat spontaneously from a body at a lower temperature to a body at a higher temperature? Now, basically second law gives answer to all these questions, and basically it excludes the possibility of constructing 100% efficient heat engine and perpetual motion machines. What are perpetual motion machines? We will come to know in subsequent slides. Basically there are two classical statements. One is known as Kelvin-Planck Statement and another is Clausius Statement. What are their statements exactly? That we will discuss in subsequent slides. But Kelvin-Planck Statement is dealing with the heat engines, and it basically excludes the possibility of constructing a 100% efficient heat engine. Similarly, Clausius Statement is dealing with refrigerators or heat pumps. Second law of thermodynamics also introduced the concept of reversibility. Moreover, it also determines the theoretical performance limits of engineering systems, means heat engines and refrigerators or heat pumps. That is, it basically gives the performance limit for the power producing devices as well as power consuming devices, that is refrigeration devices. Now, before we proceed further, we would like to introduce few terms that we will be using throughout our lectures in engineering thermodynamics. One of the important terms is thermal energy reservoir, or you can say heat reservoir. So basically, a body of infinite heat capacity to which and from which heat can be transferred indefinitely without changing the temperature of the reservoir. So basically what happens when we are studying thermodynamics, then it is convenient to consider a hypothetical body with a relatively large thermal energy capacity, means mass into specific heat of that body should be large, that it can supply or absorb finite amounts of heat without undergoing any change in temperature. Such bodies are known as thermal energy reservoir or heat reservoir or reservoir. In practice, large bodies of water such as oceans, lakes and rivers, as well as atmospheric air, they can be modeled accurately as thermal energy reservoir because of their large thermal energy storage capabilities or thermal masses. For example, many industries are dumping their heat. Many automobiles, they running on the roads of the different cities of the world, they are discharging a considerable amount of heat into the atmosphere. Even then, there is slight change in the temperature of atmosphere, and that too over the hundreds of years. So we can say that atmosphere is basically a thermal energy reservoir because it is a body of infinite heat capacity. Similarly, you must have seen that power plants are normally situated on the banks of rivers. Why so? Because for the cooling of working substance in condenser, you need gallons of water every day, and that can only be supplied by a body which is having large quantity of water. So definitely you need a river, and you must have seen that these large bodies of water, oceans, lakes and rivers, they do not get warm up as a result of heat losses or the energy that is dumped in the rivers by power plants, and they are not causing any significant change in its temperature. So you can say that these water bodies are also good examples of thermal energy reservoir. Two-phase system, they are good examples of reservoirs because They can absorb and release large quantities of heat while remaining at constant temperature. Industrial furnace can be a good example of thermal energy reservoir. The temperature of most furnaces are carefully controlled and they are capable of supplying large quantities of thermal energy as heat in an essential isothermal manner. Means temperature of the furnace will be maintained almost constant and they are supplying large amount of heat to the substance where it is desired. So industrial furnace are also examples of thermal energy reservoir. So a body does not actually have to be very large to be considered a reservoir. Any physical body whose thermal energy capacity is large related to the amount of energy it supplies or absorbs can be modeled as a thermal energy reservoir. For example, if you take an example of say heat dissipation from a TV set in a room, then definitely the air in the room can be treated as reservoir. Since the amount of heat transfer from the TV set to the room air is not large enough to have noticeable effect on the room air temperature. Have you ever felt that because TV was on for hours and because of that the air temperature in the room has risen, has increased? Definitely not. So it means room can act as a thermal energy reservoir if there is a heat dissipation from TV set. A reservoir that supplies energy in the form of heat is called a source, and one that absorbs energy in the form of heat is called a sink. So basically, source is a reservoir or a body from which heat is absorbed, means which is supplying heat. For example, high temperature body in case of heat engine, or you can say low temperature body in the case of refrigerator or heat pump. That is basically source because that is supplying heat. Sink is basically a reservoir body to which heat is rejected. For example, low temperature body in the case of heat engine, that is sink because heat is dumped into it, or high temperature body in the case of refrigerator or a heat pump. That is also an example of sink. Now, a body of finite heat capacity to which and from which heat is transferred, the temperature of the body changes, that is known as thermal body, and it is opposite to TER, thermal energy reservoir, because thermal energy reservoir is a body of infinite heat capacity, whereas thermal body is a body of finite heat capacity. Means if you are supplying heat to thermal body, its temperature will change, and even if you are extracting heat from the thermal body, its temperature is going to change because thermal body is a body of finite heat capacity. It's like thermal energy reservoir is like you take a mug of water from an ocean, then its level is not going to change because that is a thermal energy reservoir. But thermal body is like a bucket. If you take a mug of water from a bucket, the level of water is going to change. So I think this example will clarify the difference between the two, that is thermal body and thermal energy reservoir. Now, as I told you earlier also, that as far as thermodynamics is concerned, then we are having two types of devices. One is power producing device and another is power consuming device, which basically gives us cooling effect by consuming power. So heat engine is basically power producing cycle or power producing device. So how to define that? Heat engine is a device that operates in a thermodynamic cycle. and does a certain amount of positive work through transfer of heat from high temperature body to a low temperature body. We are going to discuss these terms multiple times in our subsequent slides and in subsequent lectures. Like heat engine is basically a device that is operating in a thermodynamic cycle. Means definitely the working substance is executing a cycle. The working substance of the heat engine is executing a cycle. And while heat is transferred from high temperature body to low temperature body, we are going to get certain amount of positive work. Means system is doing work on the surroundings. Now refrigerator or heat pump, they both are power consuming devices, and in both cases there is flow of heat from low temperature body to high temperature body. But even then there is certain difference which we are going to clarify to you in subsequent slides. So basically refrigerator is a device that operates in a thermodynamic cycle and requires a certain amount of input work while transferring heat from low temperature body to high temperature body or reservoir. The objective of refrigerator is to cool the space or region, while heat pump is used to heat up the space. So in both the cases, the flow of heat will be from the low temperature body to high temperature body, and it requires certain amount of input work. The objective of refrigerator is to cool the space, while the objective of heat pump is to heat the space. Now, heat engines is the term that is referred to cyclic devices which are producing a certain amount of positive work while heat is transferred from the high temperature body to the low temperature body. So this definition we have discussed. Now, there are several types of heat engines, though they differ considerably from one another, but there are certain characteristics that are common for all the heat engines. The first one, they receive heat from high temperature source, and the source could be solar energy, oil furnace, nuclear reactor. Second, they convert part of this heat to work, and this work should be shaft work. They reject the remaining waste heat to a low temperature sink, and the sink could be atmosphere, rivers, etc. Fourth, they operate on a cycle. So heat engines and other cyclic devices usually involve a working fluid or working substance to and from which heat is transferred while undergoing a cycle. This fluid is called either working fluid or working substance. So basically this working substance or working fluid is serving as a means of energy exchange. Means if heat is supplied to the system, it means heat will be supplied to the working substance. If system is losing heat, it means nothing but working substance or working fluid is losing or rejecting heat. Now, there could be good examples of heat engines and there could be bad examples of heat engine. Okay, for example, internal combustion engines and the gas turbines and car engines, they are sort of bad examples of heat engine. Why so? Because all these devices, means internal combustion engine or gas turbine means open cycle gas turbine, or car engine, they basically operate in a mechanical cycle but not in a thermodynamic cycle, since the working substance, that is the combustion gases, does not undergo a complete cycle. Instead of being cooled to the initial temperature, the exhaust gases are purged out, they are taken out, and they are replaced by fresh air and fuel mixture at the end of the cycle. Now the best example of heat engines is the steam power plant, which is an external combustion engine. For example, the steam power plant operating on Rankine cycle is the best example of the heat engine. That is, combustion takes place outside the engine, and the thermal energy released during this process, means during the combustion, is basically transferred to the steam as heat. This is basically the schematic diagram of steam power plant or Rankine cycle. The steam power plant or Rankine cycle is containing basically 4 components. And these 4 components of the steam power plant involve mass flow in and out. And so therefore, when they are considered individually, they should be treated as open system. But when these components together with the connecting pipes contain the same fluid and work as a combination system, then it will be the example of a closed system, because no mass enters or leaves this combination system, which is shown here on the slide. And you must be recalling that for a closed system undergoing a cycle, the change in internal energy is 0, and therefore the net work output of the system is also equal to the net heat transfer to the system. As you must have studied, the cyclic integral of the heat transfer is equal to cyclic integral of the work transfer for a control mass, for a fixed mass that is undergoing a cycle. So here in this case, H2O is that working substance which is undergoing the cycle. A fixed mass of H2O is undergoing cycle. So definitely that Joule's statement is applicable over here. Now, how this steam power plant that is operating on Rankine cycle works? Basically, the working substance is H2O. Now this pump or feed pump is basically raising the pressure of the feed water which is there as saturated liquid. So basically that is raising the pressure of that feed water, and that is supplied to the boiler. Now in the boiler, heat is supplied to this working substance, that is H2O, and that heat is coming from any energy source. It could be a furnace, it could be nuclear reactor, it could be any source of energy, but heat has to be supplied from an external source, external energy source. Okay, so this QH amount of heat is supplied to the steam, or you can say to the working substance, whether it is in the form of saturated liquid state or saturated vapor state, whatsoever. So that amount of heat has to be supplied to the steam in the boiler from a high temperature energy source. It could be furnace, it could be solar energy, it could be nuclear reactor. Now when this heat is supplied to the steam, or you can say working substance in the boiler, its enthalpy will increase, its heat content will increase. Okay, so when this steam having high enthalpy value, definitely it could be superheated vapor, superheated steam. So when this goes to turbine, so what will happen in turbine? There will be expansion of this steam, and I have told you that turbine is having two sets of blades, that is fixed sets of blades and moving sets of blades, and that is basically causing its expansion, ultimately causing the shaft to rotate. So basically turbine is generating work or power. Now this turbine, when coupled to the generator, will generate electricity. Now because of the expansion, the pressure of the steam drops. Moreover, its enthalpy value also decreases, because it is this enthalpy value decrease that has transformed in the useful work, or you can say the turbine work. Now the steam coming out of the turbine, which is having low enthalpy value, it is still having a significant enthalpy value, and the condition of the steam is you can say either superheated or it is very close to saturated vapor condition. So it means it has to be condensed before it is sent to pump, because pump handles only liquid. So you cannot eliminate condenser over here. Condenser has to be there because turbine cannot discharge the steam to pump directly. It has to be passed through condenser first. So basically condenser is changing its state from saturated vapor to saturated liquid. And when it has got converted to saturated liquid, it goes to the feed pump, where it which is raising basically its pressure so that it is going to the boiler. So basically QH is the amount of heat supplied to the steam in the boiler from high temperature source, that is furnace. QL is the amount of heat rejected from steam in condenser to a low temperature sink. It could be atmosphere, it could be river, etc. Now WT is the amount of work delivered by steam as it expands in turbine. And WP is basically amount of work required to compress water to boiler pressure. So you can say net work could be turbine work minus pump work, as well as QH minus QL. It is basically because this working substance is executing a cycle, and therefore the cyclic integral of heat transfer is equal to cyclic integral of work transfer. So what is cyclic integral of heat transfer over here? QH plus minus QL, that is QH minus QL. And what is the cyclic integral of work transfer? WT plus minus WP, that is WT minus WP. So now thermal efficiency, which is the ratio of net work done upon heat supplied, so that can be written as QH minus QL upon QH, which ultimately becomes 1 minus QL upon QH. We all know that heat is transferred in the direction of decreasing temperature, as we have experienced from our daily life. That is from high temperature medium to the low temperature ones. The heat transfer process occurs in nature without requiring any devices. The reverse process, however, cannot occur by itself. Means heat cannot flow from low temperature body to high temperature body spontaneously by its own. The transfer of heat from a low temperature body to high temperature body requires some special devices called refrigerators. So refrigerators like heat engines are cyclic devices. The working fluid used in refrigeration cycle is called refrigerant. The most frequently used refrigeration cycle is the Vapour Compression refrigeration cycle, which again involves four main components: compressor, a condenser, an expansion device, and a evaporator. We are going to show you the schematic diagram in the coming slides. So the refrigerator and heat pumps are thermodynamically performing the same function. There is no difference between the two, except that of the objective. In both the cases, heat is flowing from low temperature body to high temperature body, and both require input output. In the case of refrigerator, the objective is to cool the space, whereas in the case of heat pump, the objective is to heat up the space. It is somewhat like this: the air conditioner, which is cooling a particular room or space during summers, is working like a refrigerator, and the air conditioner, which is heating up a room or a space in the case of winter season is working like a heat pump. Now, whatever may be the device, we are always interested in evaluating its performance. Now, in the case of the work producing device or heat engines, the parameter to evaluate or to assess the performance was thermal efficiency. And basically, thermal efficiency is a measure of how efficiently a heat engine converts the supplied heat into the work. So basically, that is because heat engines are built for the purpose of converting heat to work. And the engineers or the scientists are constantly trying to improve the efficiencies of these devices, since increased efficiency means less fuel consumption and thus lower fuel bills and less pollution. So similarly, for the power consuming devices, that is refrigerators or heat pumps, the term that is used to evaluate or assess their performance is nothing but coefficient of performance. Now, the coefficient of performance for the refrigerator is that what is the amount of heat that has been taken out from the low temperature body divided by the amount of input of work. So basically it is Q naught upon W, that is COP of the refrigerator. Now, by the Joule's statement, as the cyclic integral of heat transfer is equal to cyclic integral of work transfer, so work will be equal to Qk minus Q naught. So that is why COP of refrigerator is put as Q naught upon Qk minus Q naught. And if you divide numerator and denominator by Q naught, we will have the expression 1 upon Qk upon Q naught minus 1. Similarly, for the heat pump, as the objective is to heat up the space, so COP of heat pump will be the amount of heat that is supplied to the space that has to be heated divided by the total work. So it will become Qk upon Qk minus Q naught, and ultimately when we divide it both numerator and denominator by Qk, the term reduces to 1 upon 1 minus Q naught upon Qk. And always note that whichever may be the cycle used for the refrigerator or heat pump, whether it is reversed Carnot cycle, whether it is compression, vapor compression refrigeration cycle, COP of heat pump will always be equal to COP of refrigerator plus 1. Now, question arises in our mind, as in the case of heat engines, we used to wonder or we used to ask questions like, can we have a heat engine that is having efficiency of 100% that can convert the heat supplied totally into the work? Can we have that? Similarly, for the heat pumps and refrigerators, we always are interested to know, can we build a refrigerator or a heat pump that is having coefficient of performance is equal to infinite, means which is requiring no input of work, zero input of work? Can we have that? If we are going to transform this into reality, then we will have no electricity bill for our refrigerators, for our cold storages, for our ice plants. And that will be a wonderful gift for us. So this is basically the schematic diagram of vapor compression cycle. And there are 4 devices: evaporator, compressor, condenser, and expansion valve. The refrigerant enters the compressor as a vapor and is compressed to the condenser pressure. It leaves the compressor at a relatively high temperature and cools down and condenses as it flows through the coils of condenser by rejecting heat to the surrounding medium. You must have seen in old refrigerators a network of condenser tubes where you must have felt somewhat hot while you were drawing your hand near to it. So basically that was condenser, and there was basically fins over that was enhancing the heat dissipation. Now the refrigerant from the condenser, the refrigerant coming out of the condenser enters a capillary tube where its pressure and temperature drop drastically due to throttling effect. Now this low temperature refrigerant then enters the evaporator where it evaporates by absorbing heat from the refrigerated space. So basically this refrigerant in the evaporator is nothing but basically it is the freezer coils. So basically the freezer portion is the evaporator. So the working substance, that is the refrigerant, is getting evaporated by absorbing heat from the refrigerated space. Means if you have put say water in ice tray, so that water has to be solidified, so that has to reject some heat to get solidified, and that heat has to be absorbed by the refrigerant which is flowing through the evaporator coils. So the cycle is completed as the refrigerant leaves the evaporator and re-enters the compressor. In a household refrigerator, the freezer compartment where heat is absorbed by the refrigerant serves as the evaporator, as I've told you, and the coils usually behind the refrigerator where heat is dissipated to the kitchen air serves as the condenser. Now Q0 is the magnitude of the heat removed from the refrigerated space at temperature T0, and Qk is the magnitude of heat rejected to the warm environment at temperature Tk, and W net is the net work input to the refrigerator. This expansion valve, or you can say the throttling valve, is doing no work. So net work is basically the work input to the compressor itself, because any other device other than the compressor is involving no work, input or output. So basically net work is the nothing but the work input to the compressor. Now this is basically the refrigerator, and here the object of the refrigerator is to remove heat Q0 from the cooled space, and that is Q0. So that is the sole objective of the refrigerator. For this heat to be taken out from the refrigerated space and to be dumped in the warm environment, which is at temperature Tk, you require input of work. So the desired output is nothing but Q0. And what is the required input? Nothing but W. That is basically causing the compressor to work. So the COP for the refrigerator will be Q0 upon W, and W will be Qk minus Q0. Another device that transfers heat from low temperature body to a high temperature one is the heat pump. Refrigerators and heat pumps operate on the same cycle but differ in their objectives. The objective of the refrigerator is to maintain the refrigerated space at a low temperature by removing heat from it. Discharging this heat to a high temperature medium is merely a necessary part of the operation, not the purpose. The objective of a heat pump, however, is to maintain a heated space at a high temperature, and this is accomplished by absorbing heat from a low temperature source, which is nothing but a well water or a cold air, outside air in the winter, and supplying this heat to the high temperature body such as house or a room. The measure of the performance of a heat pump is also expressed in the terms of coefficient of performance, and again it is the ratio of desired output and required input. So what is the desired output over here? It is the amount of heat that is being given to the space to be heated. So Qk is the desired output, and what is the input that is required? Nothing but compressor work, that is W. So Qk upon W is the COP of heat pump. Now by the Joule's statement, cyclic integral of heat transfer is equal to work transfer. So work here is involved is nothing but W, and the cyclic integral of heat transfer will be Qk minus Q naught. So the COP of heat pump is Qk upon Qk minus Q naught. Here we have considered the magnitudes of the heat transfer only, not their actual signs. Before I state the Kelvin-Planck statement, one question arises, though we have talked a bit about it earlier, but even then we can discuss it just now also. In a steam power plant, the condenser is the device where large quantities of waste heat is rejected to rivers, lakes or the atmosphere. Then question arises, can we just not take the condenser out of the plant and save all that waste energy? The answer to this question is unfortunately a firm no, a big no, for the simple reason that without a heat rejection process in the condenser, the cycle cannot be completed. You know that cyclic devices such as steam power plants, they cannot run continuously unless the cycle is completed. This energy, which we call the waste energy, which is rejected to the low temperature body or to the sink, it cannot be recycled. Thus, it is clear that every heat engine must waste some energy by transferring it to a low temperature reservoir in order to complete the cycle, even under idealized conditions. The requirement that a heat engine exchange heat with at least two reservoirs for continuous operation forms the basis of the Kelvin-Planck expression of the second law of thermodynamics. So now it is clear that basically Kevin-Planck statement is pertaining to the operation of heat engines. So it says that it is impossible for any device that operates on a cycle, means thermodynamic cycle, to receive heat from a single reservoir and produce net work. It means a heat engine must exchange heat with a low temperature sink as well as high temperature source to keep operating. If we recall the expression for the efficiency that we discussed few slides back, it was 1 minus QL upon QH. When QL is 0, only then we can have a heat engine that can have 100% efficiency. But as we have discussed just now, that it's not possible to have the value of QL equals to 0. QL must have some finite value, means it is pertinent that a heat engine must reject some heat, some finite heat to the low temperature reservoir or to the sink. So it implies that it is impossible to build a heat engine that is 100% efficient. In the coming discussion, we will also come to know that in the case of reversible heat engine or Carnot heat engine, we can have efficiency expressed in the terms of temperature. So 1 minus QL upon QH, the expression of efficiency will become 1 minus TL upon TH. So there we come to know that the efficiency of heat engine can either be increased by decreasing the value of TL or increasing the value of TH. Means there are two ways of increasing the efficiency of heat engine. Either you decrease the temperature of the low temperature reservoir, that is sink, or you increase the temperature of high temperature reservoir or source. But even then, there is certain limitation because of some metallurgical conditions and all that, and operational condition, that we cannot increase TH beyond a limit. And we are going to discuss this while we will be discussing available energy. Out of the two classical statements of second law, Kelvin-Planck statement is pertaining to heat engines, whereas the Clausius statement is related to refrigerators or heat pumps. It says that it is impossible to construct a device that operates in a thermodynamic cycle and produces no effect other than the transfer of heat from a low temperature body to a high temperature body. Means it's not possible to construct a refrigerator or a heat pump that is operating in a thermodynamic cycle and it is transferring heat from the low temperature body to high temperature body without input of work. Now, like Kelvin-Planck statement, Clausius statement is also a negative statement. Why? Because there is a word, it is not possible. Not possible. Impossible means not possible. Similar is the statement for Kelvin-Planck statement, that it is not possible. So both are negative statements, and there are no mathematical proof for both of the statements. They are just based on the experimental observations, and no experiment has ever been conducted that is basically violating any of these statements. And it is for sure, if Kelvin-Planck statement is violated, then Clausius statement will also be violated. And if Kelvin-Planck statement is obeyed, means that is valid, that is for sure Clausius statement is also valid. So we can infer that it is not possible to build a heat pump or refrigerator without external work input. The Clausius statement does not imply that a cyclic device that transfers heat from the lower temperature body to a higher temperature body is impossible to construct. In fact, it basically says that a refrigerator or a heat pump cannot operate unless its compressor is driven by an external power source, such as an electric motor. So the net effect on the surroundings involves the consumption of some energy in the form of work, in addition to the transfer of heat from the colder body to a warmer one. As discussed earlier, if Clausius statement is violated, then we can have our refrigerators operated without consumption of electricity. Means we can enjoy ice creams without the consumption of electricity. The Kelvin-Planck and the Clausius statements are equivalent in their consequences, and either statement can be used as the expression of the second law of thermodynamics. Any device that violates the Kelvin-Planck statement also violates the Clausius statement, and vice versa. Consider a heat engine refrigerator combination. So we are having basically a heat engine and also a refrigerator that are operating between the two temperature reservoirs, means hot reservoir at T1 and cold reservoir at T2. Now this heat engine is basically violating the Kelvin-Planck statement. whereas the heat pump, or you can say refrigerator, that is a normal one. Now the heat engine is having the efficiency of 100%, means whatever Q1 amount heat has been received by the heat engine, that has been converted fully into work, leading no rejection of heat to the reservoir at temperature T2. Now whatever work has been produced by the engine is supplied to the refrigerator, or you can say heat pump, means power consuming device. So now this work is supplied to refrigerator or heat pump that removes heat in the amount of Q2 from the low temperature reservoir and rejects heat in the amount of Q2 plus Q1 to the high temperature reservoir. You can see this is the Q2 amount of heat that has been absorbed by the refrigerator, or you can say heat pump, and from here the input of work, which is equal to Q1, is supplied to the heat pump. Now this Q2 plus this Q1 will make Q1 plus Q2. So this amount of Q1 plus Q2 is rejected to the hot reservoir at T1. Now the combination of these two devices will be this device. Okay. Now this is basically heat pump. How can you say that? What is the net heat exchange with the hot reservoir at T1? So Q1 plus Q2 is in this direction and Q1 is in this direction. So ultimately resultant will be Q2 in upward direction. Okay. Similarly, what is the net energy exchange with cold reservoir at T2? So only Q2 in upward direction. Right. What about the net energy exchange in the form of work? Heat engine is producing work and that is being supplied as input to the heat pump, or you can say refrigerator, right? So basically there is no net work produced by the combination devices, because whatever has been produced by heat engine has been consumed by the pump. So no net work transfer by the combination device. Okay. So what basically it is leading to? It is leading to the violation of the Clausius statement, because Clausius statement says that it is impossible to construct a device which, while operating in a thermodynamic cycle, produces no effect other than the transfer of heat from the cooler body to the hotter body. And basically this is violating this, because it is having no input of work. So this is leading to the violation of Clausius statement. Now this is another experiment that is proving, or that is demonstrating, that violation of Clausius statement leads to the violation of Kelvin-Planck statement. So we are having a refrigerator heat engine combination over here operating between the same two reservoirs. The refrigerator requires no work and it is violating Clausius statement. Let the amount of heat Q2 be transferred from low temperature reservoir to this refrigerator, and the same amount of heat Q2 is transferred to the high temperature reservoir. Let the amount of Q1, that is greater than Q2, be transferred from high temperature reservoir to the engine, and let the engine rejects heat in the amount of Q2 as it does amount of work equal to Q1 minus Q2. Because there is no heat transfer to the low temperature reservoir, the low temperature reservoir, the heat engine and the refrigerator can be considered together as a device that operates in a cycle and receive heat from a single reservoir and produce a net amount of work, thus violating the Kelvin-Planck statement. So basically what is happening over here, we are having this heat pump, or you can say refrigerator, that is violating Clausius statement because it is requiring no input of work. Q2 amount heat has been absorbed from the cold reservoir at temperature T2 and the same amount has been transferred to the hot temperature at T1. Okay, this is the normal heat engine. This is basically drawing or extracting Q1 amount of heat from the high temperature reservoir and rejecting amount of Q2 to the cold reservoir at temperature T2, thus doing net work equal to Q1 minus Q2. So basically this is normal heat engine. Now what is the net heat transfer with the high temperature reservoir? Q1 minus Q2 in downward direction as Q1 is greater than Q2. So net resultant will be Q1 minus Q2 as Q1 is greater than Q2. Similarly, what is the net energy exchange with cold reservoir or the reservoir at temperature T2? Because here Q2 is in upward direction and the same amount is in downward direction. So basically it is having no energy exchange with the cold reservoir or the low temperature reservoir. Now what is the net work transfer by the combination devices? Now this is 0 and this is Q1 minus Q2. So net will be Q1 minus Q2. So the net result is that for the combination device we are supplying Q1 minus Q2 amount to the heat engine and the same has been produced as the work. So this is basically leading to the violation of the Kelvin-Planck statement as there is no heat rejected to the low temperature reservoir. So this is how we have proven basically the equivalence of Kelvin-Planck statement and Clausius statement, that if one is violated, the other one is also violated. First we took the example of the violation of Kelvin-Planck statement, which basically led to the violation of Clausius statement, and the another example that of a device which was violating Clausius statement, which ultimately led to the violation of Kelvin-Planck statement. Frequently, the second law of thermodynamics has been stated as the impossibility of constructing a perpetual motion machine of the second kind. Now, basically, what is perpetual motion machine? So, three perpetual motion machines have been described. Perpetual means forever. So, it means the machines which are running forever, hamesha ke liye. So, what is PMM1? Perpetual motion machine of first kind. A fixed machine which could continuously supply mechanical work without some other form of energy disappearing simultaneously, thus violating the first law of thermodynamics. And this is impossible. Converse of the above statement is also true. There can be no machine which could continuously consume work without some other form of energy appearing simultaneously. Okay. So what does it say? That if any machine is continuously supplying mechanical work, it means it is being supplied some form of energy and that energy is disappearing and mechanical work is generated. Okay, so it means wherever there is some energy disappearing, it means it is appearing in some other form. Okay, converse of this above statement is also true, that it is not possible that a machine is consuming work and it is generating no other form of energy. It's not possible. Now, perpetual motion machine of second kind. A fixed machine which would extract heat from a source and then convert this heat completely into other form of energy, thus violating the Kelvin-Planck statement of second law. So that is also impossible. This we have discussed, that we are having a machine which extract heat from the source and convert this heat or this energy completely into other form of energy like work, means rejecting no heat to the low temperature reservoir. That is complete conversion of low grade of energy, that is heat, into work. and that is not possible, because if that had been possible, we would have a machine that was having an efficiency of 100%. Now, the perpetual motion machine of third kind is a fixed machine which would have no friction and thus would run indefinitely but produce no work. So that is also not possible, because every machine has got some moving parts and friction is always there. So this was all as far as the classical statements of second law of thermodynamics was concerned and its equivalence, and also the important terminology associated with the second law, like heat engine, refrigerator, heat pump, and the difference between the refrigerator and heat pump, and their performance criteria, that is efficiency and COP.